Hello my dears and welcome to Elementary, the channel that teaches you all about chemistry. This is the first video in a series called Equation Explanation, where I'll be breaking down some common equations used in chemistry, explaining the components, how to use the equation and where you might see it. Today I'm going to talk about the Broglie equation, which looks like this. It came about in 1923 when scientists were trying to make sense of how electrons could act like particles and like waves. This is the equation that links particle and wave properties, so let's break it down. Starting on the left-hand side, we have the Greek letter lambda. This stands for wavelength, measured in meters as it is the SI unit of length. Wavelength is often given in nanometers, so watch out for that conversion. This particular wavelength is called the Broglie wavelength, or sometimes the associated wavelength. Moving over to the right-hand side, we have the best thing you can find in an equation, a constant. This is Planck's constant, equal to 6.626 times 10 to the minus 34 joule seconds, so a very small number. This is an empirical constant, so it doesn't directly describe anything in real life, it's just used to make the equation work. Planck's constant is divided by mass in kilograms times velocity in meters per second. Now, if you're a physics student, this might look familiar. Mass times velocity is equal to P. P stands for momentum, so this is the momentum of a particle. Sometimes you'll see this equation written with a P, don't let that throw you off. It still stands for mass times velocity, and if you're given the momentum, you just plug it in here. Now we have all our components, it's good practice to check your units. Here Planck's constant is in joule seconds. A joule is a kilogram meter squared per second squared, so that second cancels out. Now we can see kilogram cancel, seconds cancel, 1 meter cancels, leaving meters left. So wavelength is indeed measured in meters. So this equation is used almost exclusively for electrons. That's what it was originally designed for. And because Planck's constant is so small, you need a very small mass in order to get a relevant wavelength. Electrons are the smallest subatomic particle before you get to quarks, so they actually have an associated wavelength that causes them to display wave properties. And remember, electrons all have the same mass, so if you're dealing with an electron, mass becomes a constant too. Mass of an electron is 9.109 times 10 to the minus 31 kilograms. As you can see, similar magnitude to Planck's constant. You'll either be given a wavelength and be looking for the speed of the associated particle, or be given velocity or momentum of a particle and calculate the associated wavelength. To calculate wavelength, just plug in the mass and velocity as well as Planck's constant, but to get the velocity out, we need to do a little rearranging. First multiply both sides by mv, then divide both by lambda. Now we're equal to mv, which, recall, is momentum, so you can calculate your momentum now. To get only mass or only velocity, just divide by the opposite variable to isolate your desired result. That's all for today, my dears. If you have any questions, pop them in the comments. Subscribe if you'd like to see more of my videos, and if you want more content from me right now, you can find my Substack linked in the description. All the best, and remember, it's elementary, my dear.